Now we have example 4. Example 4, we have the circuit here, and we were told that at t equal to 0, V2 equal to V0, and then for t greater than 0, Vg of t is equal to 0. Okay, this is the voltage source. When t is greater than 0, after the circuit has been turned, the switch in the circuit has been turned, Vg of t equal to 0. So find V2 of t for t greater than 0. We are looking for this V2 of t for t greater than 0 after the switch in the circuit has been turned. Okay, so, and we have been given the initial conditions. These are initial conditions, all right, at t equal to 0, V2 equal to V0. So let's get started. We do remember our continuity principles, and we do remember our KVL, we do remember our KCL. Those are the things we're going to apply here. And if along the line we need to make use of voltage division, we will do exactly that. All right, these are the basic principles that we've been applying for a while. All right, so as you can see here, at t equal to 0 plus, we can take KCL at node 1. This is this node 1 here. So the current coming in to this particular place will be negative. So if you rearrange that and you carry out that mathematically, you would obtain VI minus VG over RA. That's the voltage difference divided by the resistance here. Okay, that will give us a current coming into this particular node. So you have that here, plus the current leaving the node through RF. All right, the current leaving the node through RF. RF represents our feedback loop. This is a feedback resistance. Okay, so this is the feedback we have here. All right, so we have V1, the voltage at this particular node will be V2. Okay, so it will be V1 minus V2. As you can see, there's V2 here. So V1 minus this V2 divided by RF will give us a current, leaving this node. So that's what we have here. As we know, no current is going to come into this place. So the amplifier doesn't allow current to come in at both terminals. So we have V1 minus V2 over RF plus the current passing through this node, through the capacitor down to this place would be, normally current is supposed to be C divided T. It's supposed to be C divided T. IC is C divided T. So in this case, we still have C divided T, but the V now would be V1 minus V2, which is the voltage difference between this node, between this node and the second node where we have V2, okay, when considering current passing through the capacitor. All right, so this is what we have. If you add everything together, it will be equal to 0. And then we have been told that at t greater than 0, our VG will be equal to 0. They gave us that condition. So VG is 0 for t greater than 0. And then don't forget that our V1 will be equal to V plus, and that will be equal to 0 too. This would also be equal to V now. So this will represent V1 of 0 equal to V of 0 plus, and then those will be equal to V of 0, which everything would therefore be equal to 0 at time equal to 0. Okay, so for the ideal amp and negative feedback, these are the details we're going to have. When we go ahead and substitute our V1 is equal to 0 here, this becomes 0, okay? And then if that happens, this becomes minus VG over RF. Also, our VG is 0, so this will also be 0. So that means this entire expression here becomes 0, okay? So that's that. V1 is 0, this becomes 0. V2 is not 0, we don't know it, but it's not 0. So we have minus V2 over RF here. Here we normally are supposed to have plus C dV1 minus V2 over dt. Then what we have here, this is 0, so we have d of negative V2 dt. So if that negative comes out, if you differentiate that, that becomes minus 1. Okay, so you take that minus 1 out, what we're going to have left is going to be equal to dV2 dt. So we have minus C, that minus changes this plus to negative. That's why this is negative here. So you have minus C dV2 dt equal to 0. All right, so if you rearrange these, eventually this is what it will give you. This takes us back to our first order circuit. If you remember, we've talked about the first order circuit before now. So we have the V2 to T plus V2 over CRF equal to 0. All right. So solving for V2, what we would need to do first of all is to just integrate, okay? Just integrate. So if you integrate the V2 dt, you have just V2 left. That will be equal to integral of V2 over CRF equal to 0. So if you integrate that, what you are going to obtain will be V2 of 0 exponential minus t over RFC if you do integrate this. We have talked about how to integrate these. We've done this before, so I don't want to go over that again. If you go through the past discussions we've had about first order differential circuits, you will be able to figure these out. Eventually, V2 of 0 will be equal to V0. We know that, so you place that here, and then you have exponential minus t over RFC. The reason we have all of these in terms of symbols without real values is because in the circuit given to us, we don't know the value of C, we don't know the value of RF, we don't know the value of most of the, we don't even know the value of, those two. If we knew them, it would have been easier for us to substitute into here, and then we have the necessary values. Okay, this is a very simple example, by the way, so please go through it, understand it, and then let's move to the next example. The next example I have here is also an easy example. We're just going to quickly rush through it and then see how far we can go from there. You see, we are given this circuit and we are told to find V2. Again, this is V2 here. Find V2 of t for all t's. For all t's, okay? So when t is 0 minus, when t is 0, when t is 0 plus. For all values of t, before, during, and after, we should find V2 of t. Okay, so first of all, we want to find at t equal to 0 minus, we apply KCL to node 1, all right? So if you do that, what would we obtain? This is node 1 here. So if you apply KCL to this node, this is going to be V1 here, by the way. Don't forget this to be V1. And then this is going to be 0 because it's going to be connected to the ground, to the earth. Okay, so the voltage here will be V1 minus 0 over 205. That's what you have. It just becomes V1 over 205K. And then that's for the current coming in. And then for the current leaving here, you're going to have this V1 minus, since we are dealing with 0 minus, okay, so it's going to be V1 minus this V2. At this particular point, we are going to have V2 here. So it'll be V1 minus V2 divided by 20K. That's how they got what we have here. If you add both together, it will be equal to 0, all right? So don't forget at t equal to 0 minus, what we're going to have is that there is no current passing through the capacitor. At t equal to 0 minus, no current passing through the capacitor, all right? We're not going to work with these at all. What we'll find out is for an ideal operational amplifier, as we have discussed, V1 of 0 minus will be equal to V plus of 0 minus, which will be equal to 0. And that would be the same thing as V2 of 0 minus, by the way. So everything happening, just before the switch of the circuit is turned is going to be 0, okay? The voltages are 0. That's why you have V0, V plus of 0 minus equal to 0, V1 of 0 minus equal to 0, V2 of 0 minus equal to 0, following the feedback principle and the ideal op-amp principle. Okay, and then for the continuity of the capacitor voltage, we have always talked about the fact that V2 of 0 minus V1 of 0 minus will be equal to V2 of 0 plus. Okay, we have also talked about this before. So if you go through the previous classes we've had, we talked about all of these. As you can see here, this is V2 here. Okay, so V2 minus V1 of 0 minus will be equal to V2 of 0 plus minus V1 of 0 plus. We've talked about that, and everything will be equal to 0. Okay, and that would also be the same as V2 of 0 plus. V2 of 0 plus we've been given, that would be equal to 10. If you remember, we talked about difference amplifier the other time. So just keep all of those in mind. They will go a long way to help you. Okay, so we know that our V2 0 plus will be equal to 10 volts. So what we want to do is at KCL at node 1, when t is greater than 0, when t is greater than 0, what do we have? At that point, we have t equal to 0 plus, okay, anything greater than 0. So we have V2 of 0 plus is going to be 10 volt as given to us here. So that simply means V1 will be equal to V plus, which will be equal to 10, okay? If you use the ideal op-amp negative feedback principle and then the continuity principle, we're going to obtain these. So KCL at this particular node, node 1, would now be V1 minus 0 over 25, then it becomes V1 over 25, and then that V1, we said it is now 10 volts, so it becomes 10 over 25. Okay, so this is when t is greater than 0. This is not initial conditions anymore. So we have 10 over 25k, then plus V1 minus V2. V1 is 10, so you have 10 minus V2 over this 20k here, because we're just going to look for the voltage difference between these two voltage points, these nodes, two terminals. Okay, so we have that. Then plus this time around at t greater than 0, the current is going to be flowing through the capacitor, because this is not an initial condition anymore. So this is not going to behave like an open circuit anymore. So what you have here is the current flowing through here will be C dV dt. Okay, so you have C, which is 50 micro. dV dt will be V1 minus V2, and we know V1 is 10, so you have 10 minus V2, and then you close the bracket. When you sum all the currents up, it will be equal to 0. So when you rearrange these, what you would obtain is dV to the t plus V2 equal to 18. This is just mathematics, and we've done a lot of this before, so you can do that on your own. At this particular point, we're dealing with a first equation. What you can see here is we have a DC source here, and that DC source is 10 volts. The DC source is constant. So to find this solution, the first solution, what you would do is to assume a trial force solution, which will be equal to A. A is a random constant, and we are going to use A because the DC source here is a constant. Okay, so assume a trial force solution V2 of F equal to A. If you put that here in this expression here, what you will find is the A dt, that gives you 0, and then you have A equal to 18 left at the end of the day. With A equal to 18, you can also come up with your characteristic equation. In that particular case, the characteristic equation from here, from what we have done before now, should be very straightforward. It should be S plus 1 equal to 0. We are not going to take 18 into consideration. So for the characteristic equation, we just equate everything to 0. So we say S plus 1 equal to 0. S would be equal to minus 1. So the natural solution would be V2n equal to k exponential minus t. Normally it should be k exponential s, but our s is minus 1, so we have k exponential minus t here. Okay, so if we take it further, since we now have the natural solution and the first solution, all we need to do is combine both of them. Natural solution plus first solution will give us a total solution. So that gives us V. So that should give us k exponential minus t plus 18 volts. Okay, k exponential minus t plus 18 volts. 18 volts is the first, k exponential minus t is the natural solution. And don't forget, we were given initial conditions right from the beginning. Okay, right in the question we have initial conditions. We can use that to find the value of k. Okay, to do that, we know V2 of 0 plus is going to be 10. So at that point, our t is 0, okay, or 0 plus. Okay, so if you put t equal to 0 here, this becomes exponential 0. Then you have k plus 18 equal to 10, okay, because this V2 of 0 is going to be equal to 10. So k plus 18 is equal to 10, k will be equal to minus a. When k is equal to minus a, you can then come back and say our total solution V2 of t will be equal to minus 8 exponential minus t plus 18 volt. That would be the total solution. And then our V2, and that will be when t is greater than or equal to 0, by the way. And then when t is less than 0, of course, our V2 of t will be equal to 0, as we have determined and discussed right at the beginning here. All right. So this is another simple example that you can deal with. And then if we take it on to example 6 is also going to toll the same line with this example. So I'm going to leave you to work on example 6 on your own, and then practice it. If you have any questions about it along the line when you're practicing, you can always email me or get in touch with me or discuss it with me in the next classes, and then we can go on. This is example 6, so it's also going to toll the same line. So I'm not going to work on this. We'll fix it on your own. All right. So we'll go on to the next subtopic we have, which is the improved op-amp model. So we've been talking about a particular model before now, and you all have an idea of what that model is. If it is improved, what would it look like? the ideal model projects the fact that no current would pass through the terminals. You know, we said through the positive and negative terminals of the operation amplifier, current cannot pass through those terminals into the op amp. Okay, so in an ideal project, in an ideal model, it projects no current draw from the input source into the op amps. Okay, and the power delivered to the load at the output may be infinitely large if load resistance is very small. Okay, these are the definitions we gave, you know, when we're talking about the ideal model. Okay, in reality, there is always some current draw at the input in reality. So one way or the other, current, no matter how small it is, will be drawn from the input into the op amp. Okay, and there is a finite output resistance, and as you can see right in the model described here. All right, so you will see here that there are two resistors. We have Ri and then we have Ro. These are two resistances that have just been introduced right now. Ri will be 1 mega and then Ro will be 30 ohms. These are usually chosen as standards all the time. This is the way it is. If it's going to change, they would let you know, but this is like a standard. Typically, the values of these op amps for Ri and R0 is usually 30 ohms for R0 and then 1 mega ohms for Ri. All right. And then the op amp is usually represented with this particular circuit. So when you have an op amp, you represent it with this particular model for every single op amp that we have. All right. So let us quickly look at how this works with an example. Probably that would give you more understanding of what we're talking about. All right, let's go ahead. So here is an example here. This example, we solved it earlier. We solved this particular example earlier when we started. I think it was the first example we dealt with under this particular topic. So now we want to look at the improved model, improved version of this particular model of this particular circuit. And let's see what changes. Determine the voltages VA and VB using the improved op amp model. Okay, our A is 100,000. This time our Ri, like we said, it was going to be 1 mega ohms, and then R0 is going to be 30 ohms. Okay, these are standards. So to redraw this particular circuit, this is what you're going to have. This is the improved model, like I explained to you in the previous slide. So what you will find out here is that we have, this is our DC source. So that is the DC source here. You can see that. And then this is the input V input here. Okay, as you can see. And then, like we said, we are going to replace this op amp, this entire, you know, op amp here. We're going to replace it with, this is going to form like a terminal, by the way, a terminal eventually. So this op amp as a whole will be replaced with, you know, a new model. Let me just flip back a little so you can see the model again. So you can see here, this is the model here. You can see V in Ri and then AV in R0 here. This is the model. So that's the model that we are replicating here. So this is going to be V in, this is going to be Ri, and our Ri is 1 mega. So we'll put 1 mega here. This is going to be AV in 1, since we have two op amps here. So it's going to be AV in 1. And then this is going to be our R0 as in the model. So and since R0 is 30 ohms, we just put 30 ohms here. So again, you can look at the model. This is exactly what it looks like. Okay, so and then you can see we have the output here, V0 as a terminal output. So in this particular case, for the first op amp, the output is going to be VA for the first ampere op amp. So this VA will represent our V0 in this particular case. So that is why you can have VA here is the output of the first op amp. If we continue to represent the circuit here, we have 1 kilo ohms here, we have 10 ohms here. Again, we have another op amp here. You represent this op amp exactly the way with the improved model, the way we explained earlier with the first one. This model, you replace it, we have a voltage controlled voltage source here. This becomes AV in 2 now because we are dealing with the second op amp. This becomes our R0. Since R0 is 30 ohms, we put 30 ohms here, and then this becomes V in 2, right? So you put this here as our V in 2. Okay. So if we take it a step further from here, VB will be the final output here. So you can see the VB here as a final output. So what I want you to focus on is these are just the two things we introduced in the new model. That's one. And then this is the second one. Look at it. This one. No, not up to that. Let me claim the, yeah, okay. Let me take it like that. Okay, these are the new things we introduced into the model. Okay, so this represents the improved model 1, this improved model 2, based on the 2 operational amplifiers that we have. Every other thing you see were in the circuit. This 100 was in the circuit before, in this 10 is in the circuit. This 2 also was in the circuit before. Okay, so the only things we introduced are these new 31 mega AVIN, and then AVIN1 and AVIN2, and then of course VIN1 is here. Okay, so in the new model, this is where you put it. VIN2 is here. In the new model, this is exactly where you put it. Okay, so this is pretty much straightforward. It's not something difficult at all once you get the concept behind it. So let's take it a step further. Once we have this, every other thing becomes very easy. For this first circuit here, this first part of the circuit, what you find out is that if you apply KVL here, you have plus VIN1 minus 2 micro equal to 0. Plus VIN1 will be equal to 2 micro. So you obtain that your VIN1 will be 2 microvolts automatically. You keep that somewhere. Again, if you go ahead and use voltage division, since we know our VIN1, we know our A. So our VA will be equal to AVIN1 multiplied by the circuit parameters that we have, not just AVIN1, all right? It will be multiplied by the circuit parameters we have, okay? So now the first thing you want to pay attention to here is that we talked about voltage division, like I explained earlier. In this case, voltage division for A normally is supposed to be equal to, please follow me closely so you don't get confused here. Our VA here is supposed to be equal to the voltage source, right? Okay, it's supposed to be equal to the voltage source, okay? The voltage source in this case is going to be AVIN1. So that is why it's going to be AVIN1. That is the voltage source, multiplied by RA, if you remember our voltage division, divided by R equivalent in the circuit. Okay, this is exactly what we're supposed to do. So once you have these, you can just go ahead and apply the needful, all right? So what are you supposed to do here? What is your RA? That's the first question I have to ask you right now. What is RA from what you can see here? Our RA would be equal to, this is A here, all right? So to find RA, it would just be equal to this 10 is in parallel with this 1 mega, all right? So you keep that somewhere. 10 is in parallel with this R1 mega here. So that is how you're going to find your RA. Because the RA is supposed to be the same thing as the R that we have here for VIN2. Okay, it's going to be the same thing because they are in parallel. Okay, so the RA would be 10 parallel 1 mega. Then this guy is going to be in series with this parallel. Okay, so you add all of those together to find your RA. To find RA, it's going to be 100 plus 10 parallel 1 million. Okay, this is 10 ohms, right? Just 10 parallel 1 million, then this is 100K. Okay, so you don't mix it up. Okay, so if you have these, this is going to be your RA. So if you fix this up, 10 times 1 million divided by 10 plus 1 million, then plus 100 plus 100K. If you do that, this is parallel, by the way. What you're going to obtain is 100, then you have 009, right? So 100,009. Okay, so they calculated it eventually though, but then let's just go ahead. 100,009.999. You can just write that somewhere. All right, and this is going to be in ohms, by the way, not kilo ohms. So that is going to be our RA. All right, what is going to be our R equivalent? Don't forget, we said that VA will be A VIN1 times RA over R equivalent. Okay, so if that is our RA, what is R equivalent? Our R equivalent can be found by saying that we're looking for all the R's and the equivalent of all resistances in the circuit. Okay, so it's going to be, these guys are still in parallel, plus 100 now, then plus 30. So that means you're going to add all of this together plus these that are in parallel. Okay, these guys are in series plus these guys in parallel. Our equivalent will be will just be equal to 30 plus D. Since we are just adding 30, we have done this before, haven't we? This entire stuff here, yeah, is just our RA. So the only thing we are just adding to it is 30 to find our R equivalent. So that means our R equivalent is just going to be 30 plus RA at the end of the day, 30 ohms plus RA. If you do that, that means our R equivalent would therefore be equal to, if you had 30, it's just going to be 30 plus 9, 39. So it's going to be 100. 100,039 is what we're going to have at the end of the day. 0.999. That can continue like that. Okay, so now that we know RA, we know R equivalent, that means we can just substitute RA here, substitute R equivalent here. We know our A already, so we can just put our A in here. Our V in, we know it already to be 2 microvolts. You put, this is our V in. You just put all of these parameters into this equation, and then if you do that, mathematically speaking, you're going to obtain your VA to be equal to 0.19994. Eventually, they got their own RA. This is their own RA eventually. 1001. Let me see. 100300. Then this, they approximated. So approximated, instead of writing 09, they just wrote 10001. That's what they did from what I can see here. All right. And then here also we have 10030, 10039, right? So instead of writing 10039, they just put 40 there. So 10040. Okay, so it should be 4 here. That's exactly what I think happened here. Okay, so, and then this 0.2 is going to be A multiplied by A is 10 raised to the power 5. Micro is, we have 2 micro here, is 10 raised to the power minus 6. So 10 raised to the power 5 times 2 times 10 raised to the power minus 6 becomes 2 times 10 raised to the power minus 1. That's 2 divided by 10. That will give you 0.2. That's how they got here. So if you multiply all this together, you obtain 0.19994, right? That's the value you obtain for your VA. And then you go ahead to find your VB. How do you find this VB here? The VB is supposed to be equal to AV into, as you can see here. Again, the next thing you want to ask yourself is, how do you find your V into? I don't want you to get confused with what is here. So I'm going to show you. V into will be equal to R into divided by R equivalent multiplied by voltage source. Again, you're going to use voltage division to fix that. Okay, so your V into normally will just be V into will be equal to the voltage source for this V into now will be VA. You don't know, VA will now be this output of the first op amp will be the input for the second amp. Okay, so voltage source for that now becomes VA. So it becomes VA multiplied by R into now. R into divided by R equivalent for the entire circuit. All right. So if you can find these, then the rest is just going to be very easy. That's exactly what they tried to do here. All right. So what you see here, we have our VA calculated here already. R into will be 10. From what you can see here, this is V in 1. So this is V into. So R into will just be 10 parallel 1 mega. R into will just be this parallel combination will be our R into. So if you do the parallel combination, you would obtain something. Find it, that becomes your R into. And then your R equivalent would be everything added together. 10 parallel 1 mega plus this 100K plus this 30K will be the the R equivalent for the entire circuit. All right. So when you do that, you put the R equivalent here multiplied by your VA, and then you're going to obtain your V into. Okay. When you obtain your V into, you will not go ahead and multiply the V into by this A that we already have here, because VB is what we're looking for, not just V into. Okay, so VB is A V into. So whatever you obtain as V into, you multiply it by A, 10 raised to the power 5, and then you have your VB at the end of the day to be 1.99918. Okay, so I don't want to go through the calculation because it's just mathematics, but I've just explained to you how they got these. I had to explain to you how they got these, so you can go ahead and use it effectively to find what you're looking for. All right. Otherwise, you may not really understand what is going on here if I don't break it down like that. Okay. Let's take it a step further. So we have example 4. Another example, assume that the operational amplifier, we have A, the gain to be 10 raised to the power 5, Ri 1 mega ohms as usual, Ro 30 ohms as we know as a standard. Determine just V2 here. We have just one op amp here in this case. So you will see that we only have one, DC representation here. Every other thing you see here, there will be things that we already have in the circuit. First of all, we have these as our operational amplifier. So to represent this operational amplifier in an improved model, what you want to do is first of all to have your DC source here, all right? And then with the DC source, what you have next would be something like this. With your DC source, you're gonna have something like this here. This is gonna be your RO, all right? And then you have another terminal here, and then you are going to have something here, okay? From there, you're gonna have something here. This is gonna represent your RI, and then this is gonna go this way to your DC here, and then this is gonna go this way. And this RI will have our V in attached to it. This is where our V in would be. In this case, we're just gonna use one V in because we have only one, we have only one operational amplifier. So there's no need to have V in 1, V in 2, because we have just one sub-circuit, like one of you called it, okay? So this is what we have. This is our DC, okay? And this is V1, you can call this V1, okay? We have minus plus here, all right? So what you find out is, okay, there's another stuff here. Okay, so this is here 30 kilo ohms already in the circuit, all right? This 60 R1, there is a 60 here. Can you see this 60 here? Okay, sorry. I think I omitted something. Let me quickly fix that. This is not going to be our RI, okay? So this is just going to still be our 60 ohms here, because this is already 60K ohms. This is already in the circuit. Let me put it here, 60K. This is already in the circuit, okay? So this is going to be our 60K, all right? So what you have here is we have a feedback, by the way, but before you connect the feedback, let us connect the input here, the model, the input of the model here is going to be just here. Let me make it like this. Okay, this is going to be the input of the model, okay? This is going to be the input of the model connected here, and this can go here. So this is going to be our V in, all right? This is going to be our V in, and that V in on it is where you're going to have your RI. This is going to be our R input now, because this is going to be our V input now. This is going to be our R input, and under that you have 1 mega here, 1 mega ohms here. Everything you're looking at here is already from the circuit. So it's as good as you saying that you're creating a terminal here, you're creating a terminal here, and then you just have these here and these, VC voltage controlled voltage source here, okay? And this is negative, this is plus here, bad waves, okay? So the only thing we have not represented in this circuit is the feedback here. And the feedback connects V2 to the inverting terminal of the amplifier, all right? So from what you have, this is gonna be V2. This is the positive terminal of V2. And then this is the negative terminal of V2. The feedback is coming from the positive terminal of V2 to the negative terminal of the input, okay? So what you find out is that you can bring it from the positive terminal here, just bring it and then take it to the negative terminal of the V in, okay? So if the negative terminal of V in should be here, okay? So this could be negative and this is gonna be positive terminal of V in here. So if you want, you can actually take this out here. This particular line should be taken out. It's not going to extend downward. So it's going to just come down. We have V here, and then it stops here. Exactly. So this is exactly what they tried to, do here. Can you see that? So the only thing that came from up here is just the feedback that we had to include because it's part of the circuit, and then we'll move on like that. So once we have this, this becomes our AV in. This is going to be AV in from the model. Our A is 10 raised to power 5. So it becomes 10 raised to power 5 V in. That's how we got 10 raised to power 5 V in here. Okay. Again, this now becomes our RO. And we know our RO is going to be 30. So you put 30 ohms here. This is our RI, then you put 1 mega. This is 1 mega. You put 1 mega here. Okay, this is 1 mega. This is 1 mega. You put that here. This is RO 30 ohms. You put this here. So what else again? Every other thing here has been in the circuit before. Okay, so once we have this and we understand exactly how we got this, then the rest becomes very, very, very easy to deal with. So that means I can go ahead and clean this up. The rest will be very, very straightforward and easy to deal with once we understand exactly how that is developed and created. Okay, so let's try to fix it. This that you see here does not represent what the circuit should look like. What we should have is just a voltage source here, and then we have a resistance here. That is what we're supposed to have. So to do that, you can just quickly pull up our knowledge of Thevenin circuit. Okay, so because we are going to create a terminal here, like I explained to you, if you go back to the beginning, the model says that there has to be a terminal here. So you create like a terminal here, and then you create like another terminal here, like that. So if you have this here, you can easily convert this to, just one equivalent resistance here, and that equivalent resistance is going to be equal to the R Thevenin. Okay, once you do that, this voltage source here is also going to change to V Thevenin. Okay, so and that will be V open circuit because we're going to create an open circuit here in the new model. Okay, if you do that, your VOC will be V Thevenin, and that would just be equal to 60 divided by 90. Okay, 60 is going to be R, this R1, this is going to be the R here, divided by the R equivalent. Okay, so to do that, it becomes R equivalent will be equal to 30 plus 60, that is 90. So it's 60 over 90 multiplied by the V source. V source will be V1. Okay, so you have that as V1 here. So you have 2 over 3 V1 will be your VOC, and that will become your V Thevenin. So this voltage here will change from V1 to 2 over 3 V1. And then this will disappear once that happens, and then you only have one equivalent resistance here. That equivalent resistance becomes, since these guys are going to be in parallel, it becomes 30 times 60 divided by 30 plus 60 to get your equivalent resistance, and that becomes 20 kilo ohm. So when you redraw that circuit, you're going to have something like this. Okay, and then you still have a voltage source here, and this time around there is no longer any resistance here. You just have a terminal here. And then you have a terminal here, and then you go ahead, you have your V in, and then you continue, you have something here, and then this goes, and then this continues to the rest of the circuit, and then this goes this way. So this becomes your A, this becomes your B here, and then that goes like that. Okay, so that's exactly how to deal with these. So we have been able to take out this 60 ohms. So you have 20 here, and then you have 2 V1 over 3 here now, and then you have the rest of the circuit. All you need to do right now is just apply KVL. Apply KVL. Once you apply KVL, the entire problem is solved. Don't forget, we are just looking for V2. So if you apply KVL like this, and then you have your flow of current this way, that would mean that you have minus 2 over 3 VI, okay, because it's traversing from negative to positive, plus 20 KI. This is what we know, right? So because V here will be IR according to Ohm's law. So R is 20K, I is this. So it will be 20K multiplied by I. Then plus, if you come here, plus V in, right? So in this V in will be 1 mega multiplied by the I is passing through here. So 1 mega times I will be the V in here. So plus 1 mega, right? Times I. That will be the voltage here. And then we keep going. Voltage, the next one will still be plus. Don't forget there's still 1 mega here, right? So the same I is passing through here. That's plus another 1 mega I, right? And then if we keep going this way, it becomes plus 30 times I. That's 30 I now, not becomes plus 30I because the same current is passing through here. And then it goes down and then it becomes plus, it's traversing from positive to negative, so it becomes plus 10 raised to power 5 V in. Exactly, yeah. So if you sum everything up, KVL, everything will be equal to 0, all right? So if we have this, it simply means that this 10 raised to power 5 V in is what we have here, right? This 30 is what we have here, and this 10 raised to power 5 V in is what we have here. So that means so far what we have done, this is correct. Also, minus 2 over 3 is here, so we have that. So the only thing that gave us this 2.02 times 10 raised to power 6 is going to be what we have, 20 Ki plus 1 Mi plus another 1 Mi. All right. So this becomes very easy. 20 K is becomes now 20,000, isn't it? This is 1 million. This is 1 million. This makes it 2 million. 2 million plus 20,000 becomes 2,020,000. So you're going to have 2020. Then you have 2,020,000 here. So, and this becomes I. So everything 20 Ki plus 1 Mi plus 1 Mi is 2,020,000 I. So if you want to rewrite this here, this is the same thing as 2.02 times 10 raised to power 6, isn't it? That's 2.02 times 10 raised to power 6. That's what this is going to be. And that's exactly what we have here. 2.02 times, you can see there's dot here, this is times, okay? 2.02 times 10 raised to power 6 I. That's how they got what is in the middle here. So we got everything they got, okay, by just traveling from, you know, this particular point down to this place. Okay, what you do know is our I can be obtained by saying I will be equal to V in over 10 raised to power 6. How is that? This is V in, this is 10 raised to power 6 here. If I is passing through this place, if you already have the resistance here, 1 mega, and then we have V in here, we can say V in is going to be equal to IR. That is going to be I times 10 raised to power 6. Then if you make I the subject, I will be equal to V in over 10 raised to power 6. So that's how they got this here. So if you have this here, and then you substitute I into this particular place here, what would happen? If you substitute I into this particular equation, so wherever you see I, especially air, you put V in over 10 raised to power 6 here. If you do that and then you rearrange and recalculate, you would obtain and make V in the subject of the expression. You obtain V in equal to 2 over 3 times 10 raised to power minus 5 Vi. This is exactly what you're going to obtain if you do that. All right. So so far so good. We've been able to, you know, fix that up. Now the only thing we need to do right now is you keep that somewhere, and then you take a KVL. There are two meshes here. As you can see, we have a mesh here. Then there's another mesh here. So we have done KVL for this mesh. So we can do KVL for this mesh again, because what we're looking for is not Vn, it's V2 we are looking for, okay? So to get an expression with V2, we just take KVL in the second mesh, KVL in the second mesh here, all right? So if you do that, you have plus V2. If you check that out properly, you have plus V2, right? Is traversing from negative to positive. You have minus 10 raised to power 5 V in, right? This is what you're going to have. Then you're going this way. So this will become minus, all right? There is going to be a minus there. This is very important. And I think I should call your attention to that. Okay, it's going to be minus 30I here. Minus 30I. Why is it minus 30I? And then you equate everything to be 0. Why is it minus 30I? Don't forget there is a plus here. Okay, so the plus, there is a plus here. That simply means that the polarity here is plus for voltage, and the polarity here will be minus. That's what it simply means. So if we are going this way, it simply means that we are traversing from negative to positive for the voltage across this particular 30 ohms. Okay, it's going to be minus 30I. So if you rearrange these, your V2 will just be equal to 10 raised to power 5 V in, as you can see here, plus 30I if you take both of them to the other side of the, you know, equal to sign here. All right, if you do that, your final answer will be V2 equal 2 over 3 VI. This would mean that you substitute 2 over 3 times 10 raised to the power minus 5 VI, V1 into this place. Just bring this V in into this place. Once you bring it into this place, whatever you have left is going to be this. That simply means that 30I will be rendered almost insignificant from what I denote here. Okay, that's why they use the term approximation, the approximation sign here. 30I would eventually be rendered insignificant. Why would it be rendered insignificant? Because here you're going to bring V in over 10 raised to the power 6 here too. I is V in over 10 raised to the power 6. If you bring that in here, it becomes you have 0.00000 something. Okay, so I assume that is negligible. So that's why they took it out and then they just left it at 2 over 3 VI when you bring that. Because this 10 raised to the power minus 5 will cancel this 10 raised to the power minus 10 raised to the power 5 here. And all you have left will just be 2 over 3 VI. And that's how, you know, they left it at their final value. Otherwise, you can still write 30I here if you want. If you, you're not going to be wrong if you leave it at 30I there. All right.